Welcome everyone to this questions.
All right,
Welcome.
shortest talk ever. All right, yes, I'm done.
Welcome to this internal version of the Gemini North Talk series. Today's our guest or internal guest, our friend is Zach Hartman. Most of you know Zach. For people that don't know Zach, Zach is the mastermind behind basically every single one of your allopacans auto proposals, if you ever apply for this. And he's working on the Gemini North as a Gemini Science Fellow for 3 years now. 2 years now.
It seems like 3.
Yeah, it seems much longer in a positive way. And before you were at Ohio State, if I remember well.
Georgia State.
Georgia State. And today we're going to talk about his favorite things ever that are binary, I think, with yes, with binary or more using the Galactic Halo and much more. Thank you very much.
Yeah, thanks, Emma. Thanks for offering to let me fill this slot. We originally were like, let's do it in May, and then life got in the way, and we've moved it to now. But actually, it's really great that we're doing this right now because the timing works out perfectly with all the other talks that we have scheduled. Because a lot of these talks have actually dealt with things that are either directly related to the galactic stellar halo or are tangential in some way. So, I mean, last week we had a talk on the accretion history and chemical enrichment of the Milky Way's galactic halo. Tomorrow we have a talk about using stellar streams for cosmology. Next week, Gemini South has a talk on examining metal poor stars in the bulge, and all of these kind of tangentially relate to this. But one of the things that this talk has that is very different from all the others is all the others are looking at stars that are hundreds to thousands of parsecs away. And that's not this talk. This talk is very much centered on the solar neighborhood. In particular, we're really going to be looking within 200 parsecs of the sun. So this is a HR diagram of all the stars with proper motions greater than 20 milliarcseconds within 200 parsecs of the sun in Gaia. You can see there are a lot of high mass stars. As you go down the main sequence, you get into the K dwarfs and then the M's. We have the white dwarfs over on the left-hand side, but the overwhelming majority are low mass stars. And what a lot of these galactic halo studies are missing when they're looking at these stars that are very far away are these low mass stars that you can't really see at kiloparsecs. You can't really detect an M dwarf at a kiloparsec out using the telescopes that we've had today. And so what this study really wants to do is really examine the whole population of the galactic halo within 200 parsecs, searching for multiples. So I've been talking a lot about galactic halo stars. So what exactly are they? They're believed to be some of the oldest and most metal poor stars in our galaxy. In particular, they occupy this kind of halo in the Milky Way. You have the thin disk, you have the thick disk above it, you have the bulge in the middle, some cloud clusters floating around, and then this thin diffuse halo of stars spread around the galaxy. And the way that these systems have traditionally been detected before Gaia was really through their motions. So these stars are expected to have high velocities. And one of the ways to detect them is by using a reduced proper motion diagram, which is shown on the right here for a study from a couple of years ago. And basically what the reduced proper motion diagram is, it's effectively an HR diagram, but instead of parallax, you're taking that out and putting in proper motion as a proxy. And what this allows you to do is you can construct a semi-HR diagram, but really what it is great at doing is splitting the different populations into their kinematic groups. And so here in particular, you have the main sequence disk population above these blue points, and these blue points are actually identified halo stars and thick disk stars. And so this study was specifically focused on finding these halo and thick disk stars, identifying them and putting out a catalog, which they did in 2002. So why should you care? At the end of the day, one of the things I mentioned is they're some of the most metal poor and oldest, but that's really for a lot of stellar astrophysicists. But when you think about it from other perspectives, specifically the exoplanet perspective, for example, it becomes more of a mystery because these stars are supposed to be metal poor. And so that kind of leads to the expectation that exoplanets are going to be rare around them. And that's indeed what we're seeing in the Milky Way right now. There have been several studies over the past year using tests. We actually talked about one in Journal Club here a couple of weeks ago, a fascinating null result, where they looked at hot Jupiters and they couldn't find it in a large sample from tests. And this is another paper specifically looking at stars of potentially extragalactic origin. And so, if we find a planet around these systems, it's potentially really interesting because they're supposed to be rare. So a bunch of people are looking for them, but they still haven't found a lot. From the dark matter perspective, you can use the separation distribution of the binaries in the halo, specifically the tail of the wide binary distribution, to kind of probe constraints on potential dark matter candidates, such as machos. This was done in 2004, specifically using a smaller catalog of halo wide binaries and basically modeling out what the set tail of the wide binary distribution would look like if you had different perturbers in the galaxy. So you have 10 solar masses, 100, 1,000. And the idea is that these stars have been around for a while. These wide binaries have been around for a while. And as they've been floating around the galaxy, they've been torn apart. And so by modeling this distribution, you can put constraints on how large of perturbers you would need in order to get the observed distribution. So as I've been mentioning, from the stellar perspective, I mean, these stars represent some of the oldest and most metal poor systems that we know of. On the old front, they are excellent tracers of the dynamical history of the galaxy. Last week we heard a little bit about that with the accretion history of the galactic stellar halo. Recently, last year, there was a study released saying that instead of this nice diffuse halo, we actually think the stellar halo is now this oblong football rather than this nice circular thing. And from the chemical history point of view, they are allowing us to look back in time and see how the environment of the galaxy was during the time when these stars were being formed and tracing that up to where we are now. So from a star formation standpoint, though, there's still kind of a puzzle. I'm mentioning that this environment was much different than what it is now, and metallicity is one part of it. We really don't know what the galaxy looked like billions upon billions of years ago when these stars were initially formed. And our understanding is that it was much different than what the sun was born into. And so in particular, from this result, this was a survey about 20 years ago in 2010 from Mastagave, where they looked at a sample of population 2 stars, and they went looking for multiplicity. They went and did speckle imaging. They did follow-up. Well, I believe they did just an RV search of the literature, and they found that for population 2 stars, the distribution of binaries is different than that for normal disk stars.
A meeting?
And so, by examining this multiplicity fraction, this distribution, we can start to learn more about what's going on. And this was followed up even further by a study in 2019 from Mo et al., where they looked at solar type stars across metallicities, and they found that as you go to more metal poor systems, you have a higher close binary fraction than if you have a metal rich system. And so the blue line up here represents metal poor, and then the red line down here represents the most metal rich stars that they looked at. And so to understand the formation of these stars and the time when the galaxy was drastically different than what it is now, we really need to know what the parameters are of the systems we can see today. And in particular, we need to see what is going on in the binary population, because binaries are one outcome, one of the several outcomes of the star formation process, although you could basically say single stars and multiple systems as the two. And so we really need, if we could really define what the parameters are of the binary populations that we see today, we can provide basically constraints that models and theorists are going to need to explain how we got there from the beginnings of stars. And so what parameters do we really need? So Duchesne and Krauss, in their review about 10 years ago, said that we need to know the multiplicity fraction and orbital parameters based on primary mass across a variety of different parameters throughout the lifetime of these stars. And so in particular, I've already highlighted a couple of them. You know, the period and separation distribution one, the eccentricity distribution of binary systems can tell you how these systems formed as well. And then of course, the multiplicity fraction across stellar mass as a function of age as well will inform us a lot about what was going on in the early ages of the galaxy. And so one of the key things that we need for all of this, though, is we need the masses of these stars. And for single stars, it's very hard. But for binaries, it gets a little bit easier. And in particular, if you're looking at astrometric binaries or spectroscopic binaries, you can start to really dig into estimating and getting precise parameters for the masses on these systems. And that can lead to a whole bunch of things. It can lead to us understanding the mass ratio distribution. We can also figure out a mass luminosity relation. That has been one of the key works of a couple of different astronomers throughout the last decade, is figuring out that mass luminosity relation for the disk. But now we definitely need to expand into the halo, and then also the luminosity function of the galactic halo. You know, how many stars there are. Emma and I are working on submitting a proposal for extragalactic luminosity function, but we could still do that for stellar parameters as well. And so on the right here, what I show is a study from Elliott Horsch in 2019, where they looked at a sample of metal poor stars and determined their masses. So on the y-axis, you have the total mass, and then on the x-axis, you have metallicity. And you can see that, you know, around minus 0.5, 0, minus 1, they have a lot of systems. But as you get the more metal poor systems, they really are lacking down there. And part of this is because we don't have a lot of those identified binaries to put on this plot, and they haven't been studied for long enough to determine the masses of these systems. And so we really need to find a lot more of these systems and start putting them on plots like this in order to fully understand the halo binary population. But before we even go into talking about the halo itself and really diving into this talk, we need to spend time talking about the disk, because the disk contains the largest amount of stars in the galaxy. And there's been a lot of work on this over the past decade. Andre Tokoven at CTIO has been doing a lot of work on this. Specifically, his FG sample in 2014 was of great value to understanding the multiplicity fraction over stellar mass. And the Recons group at Georgia State has been doing a lot of work with M dwarfs, and now they're starting to get into the K dwarfs as well. And so on the right here, I show the multiplicity fraction and triple fraction. So the multiplicity fraction is the thicker lines above, and then below you have these thin lines, which represents the higher order multiples, so triples, quadruples, etc. And you can see that across stellar mass, which is on the x-axis, the multiplicity fraction decreases. So about 50% of FGK stars are in binary systems, but nearly 100% of O stars are in binary systems. And when you get to the extremely low mass systems, it's going down to 10, 20%. And so we know this pretty well now for the disk, but we don't know about the galactic halo. And so we really need to dig in and determine this for the galactic halo. And people have been trying to do this over time. So kind of digging into this, which is where we're trying to go, if we want to determine this multiplicity fraction across stellar mass for the galactic halo. And there have been some different surveys. So probably one of the big ones is Carney and Latham's spectroscopic binary survey, and that started in 1987. Over the next decade or so, they observed about 1,500 FGK stars looking for spectroscopic binaries. And what they initially found was that the disk and halo have similar spectroscopic binary fractions. And at the time, this was kind of the accepted belief for probably the next decade or so, until more studies started looking into this. And as I showed earlier, in a reanalysis, Bo et al. Found that actually it's the other way. The halo has a larger SP fraction than the disk. So this has been changing. Our idea of what's going on in this binary population has been changing over time as we've been getting more and more information. And then specifically, what's great importance to the work I'm going to be talking about is the high angular resolution imaging that has been done on this population over the past decade. So Zhao et al. In 2009 looked at 62 subdwarfs, which is another name for galactic halo stars, found that 26% of them are in binaries. mentioned Rostigave already. They ultimately determined a multiplicity fraction of 33% through a combination of speckle and literature radial velocity observations. And then finally, one of the most recent ones in 2015, Ziegler et al. Used RoboAO to look at a sample of 344 subdwarfs and found a multiplicity fraction of 12.5. Here's some of their results. You can see that they have a couple of really close binaries and a couple of really far away faint binaries. And so what we ultimately wanted to do is go in, dig into this population of halo stars that we now have, thanks to a bunch of different surveys, mainly Gaia, and SuperBlink, which I'll get to in a second, and examine these with high angular resolution imaging and figure out which ones of these systems are binaries and which ones are not. And so about, I think it was 2006, my former PhD advisor at Georgia State, Sebastian Lepine, started collaborating with Michael Rich at UCLA on a project using Sebastian's catalog SuperBlink, which was effectively one of the largest high proper motion catalogs in existence at that time, to go and look for binaries. And so over the next, it's been 20-ish years, they observed a bunch of stars. This is the sample, the updated sample now. This is now using Gaia, that they're using to grab their observation, their target stars from for the LIC-AO study that they're doing. And you can see that it's a pretty good sample of halo stars. They're below the main sequence, hence the name subdwarfs. And then, so on the left is the regular HR diagram, on the right is the reduced proper motion diagram. And so you can see that for the majority of the stars are below the main sequence. It's a good, high quality sample, although there are still some outliers. But over the past 2 decades, they've been conducting this survey, and they have over 800-ish stars that have been observed. And none of them, almost none of them, I will say, were fully reduced and analyzed before this year. They were just sitting on a Dropbox, waiting to be reduced. And about 2 years ago, kind of right after I started here, Sebastian actually sent out a call saying, hey, anybody want to help observe? And I got drafted into observing a lignite, and that led to me kind of joining collaboration and starting to examine this LIC data. And so I've been producing the Sharks data. This is the AO instrument on LIC. There was an AO instrument before called EarCal, but I've been told that it is fun times reducing that data, so I've been ignoring it blissfully for the most part. And so the Sharks data, funny enough, had a reduction code about the time when it released, about the time when I was looking to start reducing this. So I've been using what is called the Shiva reduction code from Saval et al. 2022. And so on the right here shows some of the binaries that I've detected within the survey itself, and this is the reduced data. But we really wanted to dig in. And so to dig in, we have to start fitting PSF models, which for most of the staff on the first floor here knows about, because I've probably gone into your office at some point and been like, have you ever dealt with AO data or photutils? And so I'm steadily starting to grab all of this data, reduce it, and put it through this residual image analysis to find close binaries that are hiding right now. So one of the methods that is used by this reduction code, is what it spits out, is a contrast curve. So on the x-axis, you have separation. On the y, you have contrast. And basically above this line is where you would expect to detect companions. And so we've had really good nights, so as evidenced by the night on the right here, where, I mean, at about 0.5 and below, we're reaching down to about 4 magnitudes contrast. And we have not so great nights, as shown on the left, where it's really not until about 0.71 arc seconds where we're getting down to 4 magnitudes of contrast. And so, but we take data regardless, which has been interesting reducing it, because sometimes I'll get to a bad night and I'll just be like, well, I can't see anything. So, and then you'll have a good night, and the same star will show like 2 companions, and you'll be like, oh, okay. So it's been interesting trying to look at the AO data as it comes in, but effectively what I'm doing is I'm generating, so I have the data on the left-hand side. This is using photutils right now. The net photutils generates a model, which then I can subtract off and see what's going on. Now, this right here is actually not a companion. This is a function of what happens with the AO system. It's something on that night the AO system wasn't working correctly. And so, it may look like the star has a companion right there, but in actuality, if you look over the course of the night, every single star shows that. And so at that point, you're just like, well, this is probably just an artifact from the instrument on that night, the AO correction. So we just have to take that into account. But what I've eventually started to do is I am now doing it a bunch of different ways. So this is the photutils way, and sometimes it works and sometimes it doesn't. As evidenced by this, you can see something in the model, but then the residual shows nothing. And at that point was when I was like, all right, I need something else. So what I've started to do is use a couple different functions. So first off is a MOFAT function. So a single MOFAT, we fit the data with the model, and then we get the residual, and oh, wait, there's something right there. So let's try 2. Okay, that looks a little bit better. And finally, what I've been doing is just outputting all the plots on one thing. And so over here on the left-hand side, you can see that this is about a 0.5 arcsecond binary candidate. This is the one that I was showing previously. The MOFAT fits are okay. They're not great, but you can see that there is definitely a star right next to it. And then this is a 0.56 binary candidate, a little bit off to the upper right. And so over the course, I've reduced steadily over the course of the last couple of months. I've reduced about all the data from about 2014 up to the summer of 2019, and there's about an equal amount, if not more, in the intervening years between then and now. And so they have had 147 stars. Out of that sample, 13 binaries have been detected. And so on the left, I show the HR diagram showing where our observed Lick stars are and where the binaries are. And then on the right, what I show is projected physical separation. So basically, what is the physical separation of the binary if both stars are at the same distance? Which, if they're bound systems, they should roughly be that. And so then on the y-axis, I show the distance. And then I show a couple different things here. So the red lines represent the limits of super wide, which will show up in the next slide. But the blue dashed line represents about the rough diffraction limit of the AO system at Lick. And so you can see we're almost getting down to it. We're getting down, I would say, about maybe 2-3 times what the diffraction limit is. And that could be due to the fact that we aren't getting the best seeing conditions on that night. Which, given the nights that I have observed, I think the seeing has been on average 1.5. It's been fun goings with that. But if we add in now, if we take this sample of observed stars and the sample of the binaries that they have observed, that Sebastian has selected to be possibly observed at Lick, which is basically all stars with proper motions larger than 150 milliarcseconds, you get a plot that looks like this. So as I said, I'm going to explain superwide. So superwide is a catalog that I constructed in my PhD, which is a catalog of wide binaries that was from Gaia DR2. And so effectively, what these red lines represents are the separation limits. So there was a separation limit at 3,600 arcseconds, which is this farther line out here. And then also there was a separation limit placed at 2 arcseconds, mainly because when you look at the separation distribution of binaries in superwide or in Gaia, what happens is instead of a constant climb at low separations, it turns over at some point because of the resolution of Gaia. And so we set up an artificial 2 arcsecond cutoff to kind of avoid that and to make the modeling a little bit easier. So as you can see, all the wide binaries kind of stop, although you can kind of imagine an extension going that way if we didn't have that artificial cutoff. But you can see that our AO sample is starting to dig into this area down below this cutoff and fill in that area. And if we only take the observed stars and we include any wide binaries that are in that sample, so out of the 147 stars, how many of those are in wide binaries? How many of those are detected with the AO system? We get a multiplicity fraction of about 17%. And this is higher than what the previous studies have shown, although kind of in the middle of all the previous studies. But there's also the issue that there's no real distance limit set on this. There's a bunch of selection biases in this study that are not taken into account in this number. So I kind of view this number with uncertainty, to be precise. But what ended up happening is we have all of these licked observations, and this is from Sebastian's accounting. We have 48 binary candidates over all of this, and this is also including some HST imaging. Some of these candidates are probably not real. As I was going through the LickAO data, there were some stars that were marked as binaries previously that then I looked in Gaia and they didn't have matching proper motions, so they were chance alignments, and so they are not binaries. So some of these 48 are definitely going to not be there, but this still shows that we have a lot of stars that we've observed and not a lot of binary candidates. So we still have this really low binary fraction, which we expect. The disk has about 50%. If you look at the solar type stars, the halo has less. And so what we ended up doing when I first hopped onto this,
Quick question. Probably pretty naive, but for the small separation binaries, how do you differentiate between chance projections and actual binary system? Do you have multi-epoch data?
So we do have multi-epoch data on a lot of the binaries, but for the moment, they're all basically binary candidates. I mean, as you get to smaller and smaller angular separations, the chance that you are a chance alignment decreases significantly. By the time that, when you get to within 0.1, 0.2, it's probably very likely that you are a companion. Now, for some of these, especially for the ones that are out at kind of farther separation from the AO data, I have Gaia data that shows that their proper motion, their common proper motion pairs effectively.
Okay.
But for the closer in ones, it's definitely going to take us going and re-observing them and seeing the orbital motion as they go in their orbits, which ultimately is what we want to do anyways, because we want to get the masses out of determining the orbits. So right now, I would say they're binary candidates, but some of these definitely have multiple epochs where we've seen some of the orbital motion.
Okay.
So when we looked at the LickAO data, the LickAO data is going down to 0.15 arc seconds. And this is about the time, and I've been brought up as a speckle imager through my graduate school career. And I was like, we could do better than that. And specifically, we could do better at Gemini. And Gemini has two added benefits. Number one, it is a bigger telescope, so it can go fainter, which is great because these halo stars can get extremely faint. And number two is it has a much better angular resolution than the LickAO data, both because we're operating the optical with Alipeka and Zorro, but also because you're moving from a 3-meter telescope to an 8-meter. So you just gain on angular resolution from that, but you also gain because you're in the optical versus the infrared. And so I started this program. I actually created my own sample. So they're observing their sample at Lick. I have my own sample of stars where I've done a little bit more stringent cuts. I specifically limited the distance to 100 parsecs because I wanted to get as close as I could to examining these stars. I examined the farthest range of separation that I could. I limited it to tangential velocities greater than 150 kilometers per second, which is slightly different than the proper motion cutoff. I limited it to V of 18 because that's pretty much as faint as we can go with Alipeka and Zorro. And then I also eliminated white dwarfs for the moment because I just wanted to deal with main sequence stars. So out of this sample and in Gaia, I found that there was roughly 1,100 stars. And over the past 3 years or so, we've gotten roughly 150 hours of Gemini time awarded. And if this semester goes through, then it will be roughly 200. And looking at the archive and through our proposals, we found that we have data on 174 stars. And so this is just a small sample of the results that we have so far. We've found in total 13 speckle binaries out of those 174. These are just 4 of them, some of the more interesting results. So up in the upper left, there's actually a triple system. Again, we have contrast curves. angular separation on the X, delta magnitude contrast on the Y. For the two channels of Alpec and Zorro, we use the 562 nanometer and the 832 nanometer narrow field filters. And then it's kind of hard for people in the room to see because they're so small, sorry. But in each of these physical separation or each of these contrast curves, there's also an inset showing the reduced image that Speckle Team shows. And in some cases, the blue channel fails. Speckle Team knows that the blue channel fails sometimes and they're trying to figure out what's going on with it. But we'll see if we ever, but the good thing about the Speckle data is that we've taken it. So if there are improvements in code or we want to run this data through a different code, which is another possibility I'm looking at, we have the data just available and we can go just run it through that code. And so you can see we're getting a wide range of separation and especially closer in binary. So we have a 0.06 and a 0.048 separation arcsecond binaries that, at Lick, we would never see these things. So the Speckle survey is definitely complementary and expanding the range that we're able to look at with this multiplicity survey. And so if we just look at the Speckle imaging, so on the right, I show the HR diagram with our Gemini sample on it. On the left, on the right is the detected binaries in our Speckle campaign. And then, so we have the super wide limits again. And then we also have the red dotted line is the blue channel diffraction, red channel diffraction limit. And the blue dashed line is the blue channel diffraction limit. And so, as I said, we found 13, and they're really getting down towards that diffraction limit. So much better than what we were seeing for the LickAO data. And if we add the wide binaries in that are in our sample that we've chosen to analyze, you can see that we have this widespread of separation that we're examining. And in particular, we can start to examine the properties of this system, and in particular, the separation distribution, which for the most part is relatively flat. We have 29 wide binaries out here and 13 down here. So over the course of this separation range, it's relatively flat right now, which makes some sense because we're still, this is an ongoing survey. All of these have been discovered already from Gaia. These ones that we're still searching for, we are definitely starting to discover, and they're starting to gradually build it up. So I expect that there will be a lot more down in this area as we continue this survey versus what's going on in the outer reaches of separation of the separation space. And so overall, if we look at only the observed stars that we've looked at, taking into account wide binaries and resolved triples, we get a multiplicity fraction of 10% plus or minus 2.6, which is lower than what we were seeing previously in the LickAO sample, and is also, I would say, within the errors of what Ziegler et al. Was finding with RoboAO. And I believe that part of it is because that we are now using this distance limited and very faint sample, so that we're able to see and we're able to adequately detect all of these systems, and we're getting the true, we just have a better defined sample, I think is what's going on with this compared to the Lick sample. So, but what if we combine everything? Because we want to combine, because I mean, we have both of these data sets and they look at different things. So let's combine them. Let's keep the constraints that I set forward in the Gemini sample, but let's include the AO, any of the AO images that we've observed. Then the fraction jumps up to about 11.8%. So this is kind of on order with the Ziegler results. So it's really just confirming that that their result could potentially be right. But again, this is only the raw multiplicity fraction. We're still missing a ton of data down here where we can't really see. And so what we really need to do is get an RV survey going and look at all of this. So Gaia has a whole bunch of different parameters. In particular, the RUWE, the IPD, FRAC, multi-peak, and the non-single star solutions all are supposed to kind of highlight binaries that could potentially be hiding in the Gaia data. And so we took our 18 Speckle or AO detected binaries that are in the Gemini selection, that's my selection so far. We checked them against the known Gaia parameters, and this is kind of what we got. So we have 18. So RUWD says that we should find 22. We only find 18. And that in particular, the binary sample. So of these 18, only 13 were shown to have a high RUWE. Same thing with this IPD multifrac peak, which is really just kind of looking at the fraction of double transits in Gaia, which is really great for these astrometric binaries where it isn't supposed, where you're not supposed to see a double star, and yet it finds it through this IPD multifrac parameter. In particular, we only see 3 of our binaries, or 3 of our binaries have a high IPD multifrac, and what I mean by high is it's greater than, I think I said it at 20%. And then in particular for the non-single star solutions, 0 of our binaries are in that. So I think what this tells me, for the RUWE, it says that it's a good indicator. It's not the end all be all. And this has been what a couple of our friends on the NASA Speckle team said last time when they were here. IPD multifrac, again, is another indicator, but I don't think it will say definitively whether it is a binary or not. And then I believe for the non-single star solution, that just examines a different parameter space, a different separation range than what we're observing with Speckle. So I don't necessarily think this is a warning sign or anything. I just think that we're the parameter space over which these 2 searches, the non-single star solution and the Speckle search, is kind of looking at are different. And so at the end of the day, we have this large sample, and we're continuing to apply for time, waiting on the results from the TAC and the ITAC this time around to see what we get. And so that's the Speckle survey. And so we also have areas where we can expand to, or other areas where we can go. And in particular, I'm going to highlight the work of 2 of our other collaborators on this team who have been really expanding this into space. In particular, using TESS and HST. So I want to highlight the work of Bakyoung Kim, who is working on DESI stuff at the University of Edinburgh in the UK. In particular, though, on the side, she is working on examining TESS systems, TESS halo systems to look for eclipsing binaries and fast rotators. In particular, she's found over 200,000 K&M dwarfs with tick IDs, and has been going through and looking at the test files. So of that 200,000, there's about 400 or 4,500 test light curves, and of those light curves, she's found about 20 eclipsing binaries, some of which are shown in the plot above, and then in the HR diagram over here on the right. This is actually kind of an interesting result because it's a little bit higher than what a previous result had said we should find in the galactic halo. But that could be due to some selection effects within Bakyoung's sample. But critically, actually, for some of these eclipsing binaries, 10 of them had RVs from Gaia. And so she was able to look at the kinematics of these systems and saw that most of them actually follow the thick disk rather than the thin disk, which is what is shown, or thin disk, rather than the galactic halo, which is what is shown in the plot on the right. Finally, I want to highlight the work of Melody Slonaker, who was a UCLA undergrad and is now with Mike Rich, and is now a GSU grad working with Sebastian on the same project. And what she's been really doing is searching through archival HST data, digging through other programs that didn't care about stars, about nearby foreground stars, which is very sad. But I guess people want to go look at galaxies with HST for some reason, and has been going through and finding these halo stars that are just in these images and searching for binaries. And so as you can see on the right here, here's her HR diagram highlighting the hits that she's gotten along with the Gaia resolved and the HST resolved systems. She's found about 26 binaries out of 284 systems for a raw multiplicity rate of 9%, which is roughly around what we're getting from the ground-based survey, which is very exciting to see. But critically, what she's also been doing is modeling a bunch of things, which is extremely helpful. And so in particular for her HST results, she's been modeling, if you take, say, for example, the Duquesne-Mayor distribution of binaries, which was published in '91, and kind of extrapolating, all right, we see this many binaries in our separation range. what does the rest of the, given this distribution, what does the rest of the population look like? And so she's been doing this for different stellar masses, and what she's finding is for FGK stars, she's getting around 23%. For galactic halo, which is about half of what it is in the disk right now, and then for M star, she's getting around 16%, which again is about half, because probably a lot of these M stars that she's seeing are potentially more on the higher mass side of the M dwarf regime, which is close to the K dwarfs. And because normally for the M dwarfs, I believe Winters et al. In 2019 said it was about 25-ish. But I think that was with a larger survey and wasn't including speckle results. And then I think if Winters et al. Took a slightly different selection, she got a lower fraction for the multiplicity rate of disk M dwarfs. But Melody is getting about 16% for the galactic halo, which again is lower than what we're seeing in the disk. So in conclusion, I just want to say that this project is basically designed to find these halo binaries that are floating out there that we know nothing about right now. And by studying these binaries and determining the precise parameters for this binary population, we're going to improve our understanding of not only how these old metal poor stars formed, but we can also improve our understanding of why exoplanets don't form around them, and possibly even expand it to the extragalactic realm in some way. We are conducting a multi-telescope, multi-high resolution method to search for close companions, utilizing adaptive optics, speckle, and then space-based telescopes to search for these close companions. And we are finding a multiplicity fraction that in some ways is discrepant and in other ways is similar to previous results. And up next, hopefully, is a spectroscopic survey of these systems, looking for even closer companions that we cannot find with these high angle resolution techniques. And thanks for having me here today, and any questions?
Questions? People?
Thanks, Zach. Great talk. I was just wondering, in the introduction, you said that the dark matter, like constraining dark matter models, was also part of the motivation. Have you been able, or have people been able to do this at all yet with these samples?
So I really don't know. I just remember that paper is a paper that I've known about for a while, and I haven't really dug into anything further than that paper, which is really just looking at potential macho masses. So that's something that is interesting, but I don't really know about. So sorry.
You mentioned that you need a spectroscopic survey for your stars, but I guess at lower, like not great resolution, you already have some spectrum. You have all the stuff from Gaia and all the stuff from Sloan. It's probably been targeted somehow. Can you learn something from that, or just the data quality, or not data quality?
No, you definitely can learn something from it. My big kind of hope is to kind of do a poor weather program, similar to what Vinny has done in the South, where he's looked at metal poor stars in the South using GMOS, and he said he's able to get a decent rate of velocity out of that. And what I would like to do is do a similar survey of these halo stars and take that RV that comes out of it and compare it to previous Sloan spectra or previous Gaia spectra. I think if we were to do it really well, we would need an instrument of about R of 10 to 20,000 with the lines, which Chiron would have been great for this, but we're still waiting to hear whether Chiron comes back up and running. But I think ultimately you can learn a lot from that. You can't really, so it also for Gaia really depends, because if you're using the BPRP spectra, you can't really get anything out of that. They have to have the narrow calcium triplet rate of velocity for them to have a lot of effort. And I know Andre Tokovinen's looked at using the radial velocity error to look at to find potential binaries. So that's another option.
I have a question. So I'm curious. So in the end, you find a lower multiplicity fraction in the halo than in the disk. What does that tell you about star formation, the evolution of the galaxy, dynamical evolution, these kind of things? Like if you found a equal multiplicity fraction, would that rule out some class of models versus, you know, a 2-to-1 kind of ratio?
Yeah, this is the area where I am the least knowledgeable on. It's something that I need to go and find a theorist and be like, explain this to me really well. But you know, you look at the different models. I mean, for the Bow et al. Paper where they looked at the closed binary fraction as a function of metallicity, there's some great discussion in there about how, you know, the fact that we're seeing this trend indicates that at lower metallicities, you know, the disk is a little bit, has a shorter lifetime, which is part of the reason why we are not believing that exoplanets are going to be formed. So that disks have a shorter lifetime because of the lower metallicity could also contribute to, you know, maybe we're not seeing binaries that much because the disk doesn't last that long. Although Andre could probably correct me, and I see he has his hand raised. So, but I mean, that's definitely an area where I need to dig into a little bit more. I mean, I've been focused on the observational side a lot. So yeah, hopefully I'm open to talk also afterwards. So Andre?
Hi, Zach. Thank you for the talk. I just have a comment that when talking about multiplicity fractures, they are all different. When you talk about 10% or 12%, this is your observed fraction. And when you say 46% for FG solar type disk, this is total for all periods on mass ratios. So there's a big distance between these numbers. They do not compare, and you should model. This is comment number one. Comment number two, that in your sample, Gaia sample of halo stars is depleted in binaries because there is Gaia holes, and many binaries in the halo are not in the 100% catalog because Gaia is rejecting them from parallax. This is comment number two. And comment number three, general, the white binaries in halo has been studied using Gaia data again by Huang. So they find some controversial trends like enhancement and depletion and whatnot. That's it.
Yeah, I mean, I definitely think for the Gaia selection, yes, it is definitely biased towards that, which is why I think a combination of using Sebastian's catalog SuperBlink, which was pre-Gaia, and a combination of that and the Gaia catalog is probably the best solution, because Sebastian only really cared. We're still going to miss some galactic halo stars, which is unfortunate. But Sebastian really only cared about high proper motion stars when he was making that catalog. And so I think combining those two will lead to a more complete sample. At least I hope. Yeah, in regards to the multiplicity fraction, yes, yeah, for the 46%, that is definitely for all separations, which is why I think Melody's results are the most interesting, because she's taking into account that within the model. Now, I think the model needs to be slightly different because she's using the Dukin and Mayor model, which is based on population 1 stars and not population 2. So I even think that her model is probably a little bit lower than what the actual value is. So, and yeah, I'm open to talk about this at any time, Andre. So, Tom?
Yes, early in the talk you showed the results of 3 early surveys. One was by Ziegler, which is consistent with everyone else's. And then there were 2 other surveys with smaller samples, so larger uncertainties, but still those samples, those results were way, way outside of the sort of 10% values you're getting. Is there an explanation for why they gave such large binarity percentages?
I think it is in the difference of the selection. So a lot of these were pre-Gaia, so they didn't have the distances. So they were depending a lot on tangential velocity cuts. Well, really just velocity cuts in general, using the reduced proper motion diagram, and that method and that way in particular has a bias where if your cuts are off, you're going to eliminate a lot of binaries that are overluminous because they're binaries, because there's another companion there, and so that will cut off a portion of them there. So I think that's a little bit of the answer, but it's also, but I think there's also a number of other selection effects as well.
More questions? Emma, nice talk. What is the ultimate survey you would like to have to answer all your scientific questionnaire? Do you want to have like a volume limit, a luminosity limit, a separation limit? What would be your dream?
My dream are volume limited surveys. I think I inherited that from Todd Henry at GSU, who's like always about 25 parsec sample, and now I think he's going out to 35 and 50. So I think a volume limited survey is my ultimate dream, which is why I chose 100, because for the most part, I mean, Gemini can reach a large majority of the stars out to 100 parsecs. And I think there are other telescopes coming online that will definitely help with that as well.
I guess if you have more questions, I think Zach is going to be around for the next year and a half. So take your time. Thanks, everyone. Thanks, Zach, again.
Thanks a lot for coming, and thanks for the great comments.
See you tomorrow.